Within the permafrost in Arctic regions of the Earth, large amounts of methane are trapped within the ice as methane hydrate. CH4X-H2O methane makes up about 13.4% of the mass of methane hydrate. Scientists are concerned that global warming will melt the permafrost, releasing large quantities of methane into the atmosphere. Part A. The HOH bond angle in ice is about 109 degrees, but about 105 in gaseous H2O. Explain why there's a difference. The first thing we need to understand about this question is what a bond angle of 109 and 105 degrees means. 109 degrees, well, that's a tetrahedral shape, and that's a specific name of a shape of molecule that you'll need to learn. And it means that it has 4 bond pairs. 105, well, that's a non-linear shape of the molecule, and it has 2 bond pairs and 2 lone pairs. The first thing we need to write in our 3 marker is that ice forms more hydrogen bonds than water or gaseous H2O. And that's talking about its properties, and hydrogen bonding is a type of intermolecular force. Secondly, we need to write that water has 2 bond pairs and 2 lone pairs. Now we're talking about the shape of the molecule and linking to the question. And finally, we need to explain why there's a difference. Lone pairs repel more than bonded pairs. This is a statement that you'll need to learn whenever talking about shapes of molecules, because it's a set statement that I'd recommend writing in anything where you're asked to describe a shape of a molecule. So, again, to get these 3 marks, we get 1 mark for writing that ice can form more hydrogen bonds, a second mark for saying that water has 2 bonded pairs and 2 lone pairs, and our 3rd mark for linking together and saying that lone pairs repel more than bonded pairs. B. Why are scientists concerned about the release of methane into the atmosphere? Well, methane is a greenhouse gas and therefore contributes to global warming. So that is our set statement that we're going to write to get our mark for this question. So writing contributes to global warming, we'll get our mark. C. Determine the formula of methane hydrate, CH4X-H2O. In the formula, show the value of X to 2 decimal places. Above, I've copied the beginning of the question because it has a key piece of information that we need to use in part C. And that information is that methane makes up about 13.4% of the mass of methane hydrate. So this question is asking about percentage composition by mass, and to do that we need to take the percentage and divide by the RFM of methane because it's the percentage of methane. The RFM or relative formula mass of methane is 16 because it's 12 plus 4, 12 from the carbon, 4 from the hydrogen, and then it's equivalent to 100% or 16 plus 18x, 18 coming from the RFM or relative formula mass of water. If we rearrange this, we get 13.4 multiplied by 16 plus 18x equals 100 multiplied by 16. Expanding the brackets, we get 214.4 plus 241.2x equals 1600. Then, continuing to rearrange again, 241.2x equals 1385.6, and that makes our x 5.74. So, when writing the formula, we need to have CH4 dot 5.74 because 2 decimal places, H2O. For this question, you get a mark for the correct formula, and you get a mark for your first expression using the percentage composition of methane and making it equivalent to 100%. D. Calculate the volume of methane in decimeters cubed that would be released from the melting of each 1 kilogram of methane hydrate at 101 kilopascals and 0 degrees Celsius. Give your answer to 3 significant figures. This question is asking us to use the ideal gas equation, which is PV equals nRT. If I write the units for this equation, temperature, or T, is in Kelvin, which is the degrees Celsius plus 273. R is the ideal gas constant, which is 8.314. You get given this on your data sheet in the exam. N is number of moles. V is volume measured in meters cubed. And P signifies pressure measured in pascals. Firstly, with this question, we need to work out the number of moles of methane hydrate. We do this by taking our mass of 1 kilogram, turning the kilogram into grams by multiplying by 1,000, and dividing by the RFM of methane hydrate. So 12 plus 4 plus 5.74 times 18, 18 being the relative formula mass of water. This gives us the number of moles at 8.38 moles. Then we need to rearrange our ideal gas equation to get volume. So rearranging, we get nRT divided by P. If we plug in our numbers, 8.38 multiplied by 8.314 times 273, because our degrees Celsius is 0, divided by 101 kilopascals, we want it in pascals, so we times by 1,000. And that gives us the volume in meters cubed at 0.188 meters cubed. But we want it in decimeters cubed, so converting this, we get 188 decimeters cubed. And that is our answer for part D. For the marks for this question, you get a mark for working out the number of moles, a mark for rearranging the ideal gas equation, and a mark for plugging in your numbers. The final mark is for converting meters cubed into decimeters cubed. E. Suggests why some industries are interested in the presence of methane hydrate in regions of the Earth. Well, the answer for this question is for fuel, because methane hydrate is a powerful fuel source. The mark scheme would also accept energy. So to get the mark for this question, we just need to write for fuel or energy. Both are acceptable for this question. A student plans to determine the enthalpy change of reaction 3.1 shown below. This enthalpy change can be determined indirectly using Hess's law from the enthalpy changes of reaction 3.2 and reaction 3.3 shown below. We're given the enthalpy change of reaction 3.3 as negative 57.6 kilojoules per mole. The student will determine the enthalpy change of reaction 3.2 as outlined below. Weigh a bottle containing Na2O solid and weigh a polystyrene cup. Add about 25 centimeters cubed of water to the polystyrene cup and measure its temperature. Add the Na2O solid, stir the mixture and measure the maximum temperature reached. Weigh the bottle or the empty bottle and weigh the polystyrene cup with the final solution. We're given the mass readings and temperature readings and told that the density and specific heat capacity C of the solution are the same as for water. Part A. Calculate the enthalpy change of reaction 3.2 and the enthalpy change of reaction 3.1. Show all your working. By indirectly using Hess's law, this question's meaning we can combine enthalpy change values to get an overall enthalpy change value. So that means in the context of this question, the enthalpy change value of reaction 3.1 will equal the enthalpy change value of reaction 3.2 plus 2 of the enthalpy change values of reaction 3.3. We know this because if we look at reaction 3.2 and 3.3, we can combine them to get reaction 3.1, but we need to times 3.3 by 2 because if we look at the molar ratios, we have 2 HCl and 2 NaCl in reaction 3.1, but in reaction 3.3 we've only got 1, hence we need to times by 2. In this question we're going to be using the equation mc delta T equals Q, where Q is measured in joules. We're told in the question that the density and specific heat capacity C of the solution are the same as water. Now, in our data sheets, we get given the specific heat capacity of water, and it's 4.18. This is a value you don't need to know as you get given it in the exam. If we start by working out the mass of Na2O using our mass readings, we would do 16.58 minus 15.34. Typing that into the calculator, we get 1.24 grams. Then, working out the mass of solution, we would take our 47.33 grams and minus it from our 21.58 to give us 25.75 grams. Then, working out our temperature change, or delta T, we take 55.5 and minus 20.5 to give us 35 degrees Celsius. Plugging this into the equation, mass would be the mass of solution because that's the thing that's having its temperature measured and temperature change. So 25.75 multiplied by 4.18 multiplied by 35 would give us 3,767.225 joules. In the question, we use kilojoules per mole, so we need to turn this into kilojoules. 3.767225 kilojoules. Next, we need to work out the moles of Na2O. To do this, we need to take the mass, 1.24, and divide by the relative formula mass of Na2O, which is 23 times 2. 23 is the relative formula mass of Na, plus 16, which will give us 0.02 moles of Na2O. So we're working out the enthalpy change of reaction 3.2 here, and we do that by taking our kilojoules, 3.767225, and dividing it by our moles, 0.02, which gives us 188. We need to make sure we put a negative because this enthalpy change is exothermic. And then our units, kilojoules per mole. Then for reaction 3.3, we know that enthalpy change value, so we can work out reaction 3.1. So the enthalpy change of reaction 3.1 is equal to minus 188 plus 2 times minus 57.6, which is the enthalpy change of reaction 3.3, which gives us minus 303.2 kilojoules per mole. In this question, the asterisk on the A means it's a level response question, so you can spot for these in the exam, which means you get marks for detail. You'd get marks for working out your masses of Na2O and solution, a mark for your temperature change, using the MC delta T equation, converting your units, and then a mark for the correct values of reaction 3.2 and reaction 3.1, their enthalpy change values being correct. So that will get you 6 marks for this question. B. The uncertainty in each temperature reading is plus minus 0.1 degrees Celsius. The uncertainty in each mass reading is plus minus 0.005 grams. Determine whether the mass of Na2O or the temperature change has the greater percentage uncertainty. show all your working. If we start by working out the percentage uncertainty of the mass of Na2O, we work out percentage uncertainty by taking the uncertainty of each reading, 0.005 grams in this case, and then we multiply by the amount of times we've used a mass reading, in this case twice. Now I've rewritten what we worked out as our mass of Na2O, which was 1.24, so we divide it by 1.24. Then we multiply by 100 to get a percentage. In this case, our percentage is 0.81% for mass. Then for temperature, we use a similar approach. 0.1 this time is our uncertainty for each reading. We then multiply by 2 because we've used 2 temperature readings to work out temperature change. I've rewritten temperature change as 35 degrees Celsius. We then multiply by 100. That gives us a percentage uncertainty of 0.57%. So mass has a greater percentage uncertainty. Percentage uncertainty is something that comes up in most PAGs, and so it's a really good idea that you know this equation, practice using it, because it's a very common 2-marker for PAG questions. And in these 2 markers, you get a mark for the percentage uncertainty of mass and the percentage uncertainty of temperature. You don't get a mark for linking to the question, but it's always a good idea to, because in a level response question, that would get you a mark. Level response questions are longer answer questions, which this is not, but it is good practice. C. Suggest a modification to this experiment using the same apparatus which would reduce the percentage errors in the measurements. Explain your reasoning. Again, this is a very common 2-mark question to do with mass PAGs. The set answer that you should learn is a greater mass. You could also use a greater temperature change. Both would reduce percentage uncertainty. And the reason for this is because if you have a larger denominator, that will reduce the number that you end up with, and a greater mass and a greater temperature change will be the denominators when working out percentage uncertainty, and so they will reduce the percentage errors if you have a greater mass or temperature change. In this question, you get a mark for saying greater mass and a mark for saying greater temperature change. D. Sodium oxide Na2O can be prepared by the redox reaction of Na, NO2 and sodium metal. Nitrogen gas is also formed. Part 1. What is a systematic name of NaNO2? So Na, that's sodium. So the first part of our name would be sodium. And NO2 is a nitrate ion. So sodium nitrate is the answer for part 1. You get a mark for getting this whole name correct. Then, using oxidation numbers with signs, show the element that's oxidized and the element that's reduced in this reaction for part 2. If we start by writing an equation, we would get that Na, NO2 and sodium form Na2 and nitrogen gas. We don't need to balance it for oxidation numbers because the stoichiometry does not impact oxidation numbers. But if we add oxidation numbers to each of these compounds, so if we start by looking at the individual elements, if it's on its own, it's going to equal 0. So the sodium metal and nitrogen gas would have oxidation numbers of 0. Then oxygen, that's always -2. And sodium, when it's in a compound, is always +1 because it's a group 1 metal. Now, oxidation numbers will always need to add up to 0. We can see in Na2O that's the case because it's +1 times 2, that's +2. minus 2, that equals 0. In NaNO2, we've got plus 1 minus 2 times 2, which, well, that will be minus 3. So, to make it 0, nitrogen has to be plus 3. Then, if we work out our element that's oxidized, oxidized means that the oxidation number is going to increase. So, the only element here that's oxidation number is increasing is sodium, and it's going from 0 to plus 1. Then, for reduction, or element that's being reduced, we're looking for an oxidation number that's decreasing, and the only element here is nitrogen, and its oxidation number goes from plus 3 to 0. For part 3, we need to construct an equation for this reaction. Well, we've already got part of an equation. We've got NaNO2 plus Na going to Na2O and nitrogen gas. But we need to balance this equation. If we balance this equation, we need 2, because we need 2 nitrogens for nitrogen gas. Then 6 and 4, because we need to balance the oxygens and balance the sodiums. For parts 2 and 3, as they're combined, you get, in part 2, you get a mark for the correct element oxidized and the correct element reduced, and the second mark for their oxidation numbers being correct. Part 3, the mark is for the whole complete equation being correct. This question is about the reactions of hydrogen peroxide H2O2. Part A. Hydrogen peroxide H2O2 iodide ions I- and acid H+ react as shown in the equation below. A student carries out several experiments at the same temperature using the initial rates method to determine the rate constant K for this reaction. The results are shown below. Part I. Determine the rate equation and calculate the rate constant K using units. To start, let's write a general rate equation for this reaction. A general rate equation for this reaction will be rate equals K and then each of our reagents. So H2O2, I- and H+. We then need to establish which order each of these reactants are. To do this, we look for where one reactant has increased by a certain value and the others have stayed the same. So, looking at experiments 1 and 2, I- has increased by a value of 2, and H2O2 and H+ have stayed the same. Then you look at rate. Rates increase by a value of +2 or times 2 as well. Therefore, the order of reaction for I- ions is first order. So I would have a little 1 going above its bracket. Then we continue to look. If we know that I- is first order, then when it's dividing by 2, hydrogen peroxide is increasing by times 2 and H+ is staying the same. Well, the rate is increasing by times 1. It's not really changing, or it isn't changing. And if we know that I- is first order, we would expect rate to half. But it hasn't, it stayed the same. And because hydrogen peroxide or H2O2 has increased by times 2, therefore the order of reaction for H2O2 is also first order, so it would have a 1. If we continue, when H+ has increased by times 2 and I- and H2O2 have stayed exactly the same, the rate has not changed, and so the order of reaction for H+ is 0 order, so we'd have a little 0. Therefore, if we write the actual rate equation, we have rate equals K H2O2 I minus. And we ignore the H plus because H plus to the power of 0 is 1. Now we need to work out rate. We can do this by subbing in values. So if we take experiment 1, we have a rate as 2 times 10 to the negative 6 divided by the concentrations or initial concentrations of H2O2, which is 0.01 times 0.01. That gives us a value of 0.02 for our K. And then for units, well, we have moles per decimeter cubed per second over moles per decimeter cubed times moles per decimeter cubed. Then we need to cancel these out. So we can cancel out a mole per decimeter cubed, and we're left with 1 over mole per decimeter cubed s to the minus 1. Another way of writing that is mole to the minus 1 decimeters cubed per second. For this question, you get a mark for the correct rate equation, a mark for the correct K value, and a mark for the correct units. Part 2. The rate constant K for this reaction is determined at different temperatures T. Explain how the student could determine the activation energy for the reaction graphically using values of K and T. In our data sheets, we get given an equation that links all of these pieces of information together. That equation is ln K equals EA over minus RT plus ln A. So our first thing when answering this question that we need to do is tell the student to plot ln K against 1 over T. And that means that our gradient will be EA over minus R. So find gradient, and then we could also write in brackets what the gradient is, EA over minus R. And finally, to get EA, we need to times gradient by minus R, which is a value you get given in the data sheet, so you don't need to specify, but then you can write that it equals EA. For this question, you get a mark for each of the bullet points that I've drawn up here. So 1 for saying plot ln K against 1 over T, 1 for finding the gradient, and 1 for saying that the gradient multiplied by minus R equals EA. B. Solutions of hydrogen peroxide decompose slowly into water and oxygen. This reaction is catalyzed by manganese dioxide. Standard electrode potentials are shown below. Using the electrode potentials, explain how manganese dioxide is able to act as a catalyst for the decomposition of hydrogen peroxide. Your answer should include relevant equations. A way to lay this question out is by numbering the equations that we're given. If we use Roman numerals, we can refer to them later on when answering. So first we need to write the equation for reaction 1 and 2. So we can see how using Roman numerals is a good idea, because then you don't have to write them all out. So if we look at their electrode potentials, the more negative, which is 1, that equilibrium would go backwards and 2 would go forwards. So if we combine these, we would have H2O2 plus MnO2 plus 4H plus goes to Mn2 plus 2H2O plus O2 plus 2H plus. We're not finished yet. Because there's an H plus on both sides, these 2 would disappear and this 4 would turn into a 2. This is our first equation. And then if we write an equation for 2 and 3, again, looking at their directions, well, the more negative this time is reaction 2, and the more positive is reaction 3. So, writing the equation, we would have H2O2 plus 2H plus Mn2 plus 2H2O goes to MnO2 plus 4H plus 2H2O. I'm not writing the electrons here because we know that we're going to cancel them out, and if they were, like say, 2 and 4, then you would need to multiply and scale up the equations, but that's not necessary here, so we don't need to write them. And we would end up cancelling them out anyway, making them even more irrelevant. So the H plus again, the 2 disappears and the 4 becomes a 2. But also we've got 2 waters on both sides, so they would disappear as well. So our reaction equation is pretty small for this one. Now, a bit of reasoning, we would write that the electropotential for I is more negative than 2, so shifts left. And that's enough reasoning. And then to answer the rest of the question, how MnO2 acts as a catalyst, well, we can say that MnO2 is regenerated. And that is enough to get our 4 marks for this question. You get a mark for each of your equations, a mark for referring to electrode potentials and how they shift, and then a mark for saying that MnO2 is regenerated, which means that it's able to act as a catalyst. C. Peroxycarboxylic acids are organic compounds with the COOOH functional group. Peroxyethanoic acid, CH3COOOH, is used as disinfectant. Part I. Suggest the structure of peroxyethanoic acid. The COOOH functional group must be clearly displayed. So the compound that we're drawing will roughly represent a carboxylic acid. And a carboxylic acid, when we draw it out, well, displayed it looks like this. So when we're drawing a peroxycarboxylic acid or peroxyethanoic acid, we can have the CH3 group. We don't need to draw that all out because they're only asking for the functional group. And that would look like this, with roughly a carboxylic acid group being represented, but instead, because it's peroxycarboxylic acid, instead of having the carbon here bond to an OH, we've got it bonding to an oxygen and then the oxygen bonding to the OH, which makes it slightly different to just a carboxylic acid. So for this question, you need to draw the structure completely correct, having the carbon-carbon bonding together rather than carbon-hydrogen here, as I've drawn C3H rather than CH3 and having the hydrogen bonding to the carbon, because that wouldn't work. So making sure we've got this whole correct will get you the mark. Part 2. Peroxyethanoic acid can be prepared by reacting hydrogen peroxide with ethanoic acid. This is heterogeneous equilibrium. A 250 centimeter cubed equilibrium mixture contains concentrations of 0.5 mole per decimeter cubed of hydrogen peroxide and 0.5 moles per decimeter cubed of ethanoic acid. Calculate the amount in moles of peroxyethanoic acid in the equilibrium mixture. So firstly, we need to understand what this question's meaning. A key word in this question is heterogeneous. Heterogeneous means that it's in different states. We can see this in the reaction or the equilibrium that we've been given, because water's a liquid here, peroxyethanoic acid's aqueous, so is ethanoic acid and hydrogen peroxide. When writing an expression for Kc, because we're given Kc here, we use the same states. So our expression for Kc would be that peroxyethanoic acid, because we work backwards when writing an expression for Kc, over hydrogen peroxide multiplied by ethanoic acid. If we plug in values for this, the square brackets in Kc, they mean concentration, and we've got values for concentration. So rewriting Kc, we have peroxyethanoic acid over 0.5 and 0.5 again, because they're the values we've been given as the concentration of hydrogen peroxide and ethanoic acid. We also know that this equals 0.37. So if we rearrange this to get the concentration of peroxyethanoic acid, we would write 0.37 multiplied by 0.5 squared, and that gives us 0.0925 moles per decimeter cubed. If we're working out moles on its own, we would use our equation triangle NVC. A way of remembering this is Nigel's very clever, and if we were to apply this, we would take the concentration 0.0925 and multiply by our volume, which is 250 centimeters cubed. We want it in decimeters cubed, so we times by 10 to the negative 3 or divide by 1,000. That gives us a value of 0.023125 moles. In our answer, we would write this to an appropriate number of significant figures, 0.023, for example. For this question, you get a mark for writing your expression for Kc, a mark for working out the concentration of peroxyethanoic acid, and then a mark for working out your moles correctly. This question is about weak acids. Part A. Compound A is a weak monobasic acid. A student is supplied with 250 centimeters cubed solution prepared from 2.495 grams of A. The student titrates 25 centimeter cube samples of this solution with 0.084 moles per decimeter cubed of NaOH in the burette. The student carries out a trial followed by 3 further titrations. The diagrams show the initial burette readings and the final burette readings for the student's 3 further titrations. All burette readings are measured to the nearest 0.05 centimeters cubed. Part 1. Record the student's readings and the titers in an appropriate format. Calculate the mean titer that the student should use for analysing the results. The key piece of information in this question is that we need to write the titers in an appropriate format. So that's why I've drawn a table for any question like this, and it's quite common where they ask you to put something in a specific format. Tables are a really, really good idea. So if we add labels to this table, first heading could be titration, 1, 2, and 3. Then we can have our initial reading in centimeters cubed, our final reading also in centimeters cubed, and then a titer that we need to work out in centimeters cubed. If we look at titration 1, the initial reading is 0.60. You read down on the burette. The final reading is 23.15, making the titer 22.55. For titration 2, the initial reading is 23.15. The final reading is 45.95, making the titer 22.80. Notice I'm writing everything to 2 decimal places, and this is a really important skill and technique to use when doing titration readings, because you can get marked down if you don't. Titration 3, the initial reading is 10.00, 2 decimal places, and then the final reading is 32.45, making its titer 22.45. Next key piece of information is that we're looking for a mean titer. When working out a mean titer, you look for concordant results. And that is plus minus 0.10 centimeters cubed. So if we look at our titration titers, titration 1 and titration 3 have concordant titers. So when working out the mean, we do 22.55 plus 22.45 divided by 2, which gives us 22.50 as our mean titer. So for this question, you get 2 marks for drawing the table and having everything correct to the right number of decimal places, significant figures, etc. The mean titer has to be correct, that gets you another mark, and using the concordant results will get you your 4th mark. Part 2. The structure of compound A is shown below. Compound A has 4 optical isomers. Using this information and the student's results, answer the following. 1. Determine the molar mass of A and the formula of the alkyl group R. 2. Draw the structure of compound A and label any chiral carbon atoms with an asterisk. Show all your working. So here I've just taken some key pieces of information from part A. If I refer back, I can show you where I've got these. So I've taken the 250 centimeters cubed solution and the 2.495 grams of A, the fact that it was 25 centimeter cube samples that they used, and that it was 0.084 moles per decimeter cubed of NaOH in the burette. I've also rewritten the mean titer that we worked out, 22.5 centimeters cubed. So firstly, we need to work out the moles of compound A. We're going to use 2 equation triangles in this question. The first being Nigel's Very Clever, where we can work out number of moles. The second being mass over RFM times moles. And that will give us the molar mass of A, which is another way of saying RFM. So if we start by taking the concentration of NaOH, 0.084, and multiplying this by the mean titer of 22.5 times 10 to the negative 3, because we want it in decimeters cubed. Centimeters into decimeters cubed, you need to times the centimeters cubed by 10 to the negative 3, or divide by 1,000. That gives us 1.89 times 10 to the negative 3 moles of A in 25 centimeters cubed. So that means that it's 1.89 times 10 to the negative 2 moles of A in 250 centimeters cubed. So, secondly, we need to use our next equation triangle. That means taking the mass of A, 2.495, and dividing that by 1.89 times 10 to the negative 2 to give us a molar mass of A, or RFM, relative formula mass of A, at 131.7, which we can round to 132. This molar mass is the compound A plus its R group. So we can work out the relative formula mass or molar mass of the R group or alkyl group by subtracting the RFM of compound A that we can already identify. So if we look at how many carbons there are 2 carbons in the compound A that we've been given. So carbons 2. Then we look at our hydrogens. We've got 1, 2 in the OH groups and 1 coming off of this middle carbon, because each carbon has to have 4 groups attached, or 4 bonds, and this one doesn't yet, so it would have to have a hydrogen. The second one here, that has 2, like a double bond attached to the oxygen, so that has 4 bonds already. So that means we've got 3 hydrogens, And then for our oxygens, we also have 3, and that's easy enough to identify because we've got 2 in the OH groups and 1 in our carbonyl group. So we subtract the relative formula mass of our compound A, or partial compound A. That would be 12 times 2 to represent carbon, plus 3 to represent hydrogen, and plus 16 times 3 to represent the oxygen. That gives us 57 as our RFM of the R group, which means our R group must be C4H9. So if we redraw compound A to answer the next bit of the question, which is talking about chiral carbons. So here I've drawn our R group of C4H9, and we need to label any chiral carbon atoms with an asterisk. A chiral carbon is a carbon with 4 different groups attached. If we start on the right and we look at this carbon, well, we've got a double bond attached to the oxygen. Any carbon with a double bond cannot be a chiral carbon. So it's not this carbon. Moving along, and we look here, well, this carbon has 3 groups that we can see, but it would also have a hydrogen, which we've established over here. That would make this carbon a chiral carbon atom. Moving along, if we look at our next carbon atom here, well, this also would have a chiral center because we have 4 groups attached. We've got 3 that we can see plus a hydrogen. On the ends of the molecules here and here, they would be CH3 groups, and because, well, if we drew a CH3 group, we can see that we've got 3 hydrogens and an R group. Even though the R group's different, we've got 3 hydrogens, they're all the same, so it can't be chiral centers. Similarly here, we would have 2 hydrogens because it would look a bit like this, with 2 different R groups but 2 hydrogens, meaning this carbon also cannot be a chiral carbon atom. To get the 6 marks in this question, you need to work out the number of moles in 25 centimeters cubed, convert it to 250 centimeters cubed. You get your 3rd mark for working out the RFM, or molar mass of A. You get your 4th mark for working out that it's 57, the molar mass of the R group. Working out that this is C4H9 gets you your 5th mark. Then drawing out compound A and labelling your chiral carbon atoms correctly gets you your 6th mark. Part B. The structural formula of compound A is repeated below. 2 reactions of compound A are carried out. Suggest an equation for each reaction and state the type of reaction. In your equations, draw structures of organic compounds and use R for the alkyl group. Part 1. Magnesium ribbon is added to a solution of compound A. Gas bubbles are seen and the magnesium slowly dissolves. So a key piece of information in this question is that we need to use R for the alkyl group. If we start by writing out our reactants, we have HOCHR, COOH plus magnesium, because we're reacting with magnesium ribbon, and that will produce a salt of HOCHR COO2 Mg, and then we also have hydrogen. To balance the equation, we need to have a 2 in front of our reactant to balance the 2 that we use here in order to balance the charges, because magnesium has a 2+ charge, and because we're only losing 1 hydrogen each time, means that this anion is going to have a -1 charge. So we need 2 to balance the charges. The type of reaction is a redox reaction. To get the 3 marks for this question, you get 2 marks for the correct and balanced equation and 1 mark for stating redox. Part 2. Compound A is heated with a few drops of concentrated sulfuric acid as a catalyst. A cyclic dimer of compound A forms. The key words in this question are that we're forming a cyclic dimer. I've redrawn compound A above just to help us keep track of everything in this question. We start this question by writing our equation, so let's write out compound A as we've done in part 1. HOCHR We can write our sulfuric acid if we want over the arrow. This we're going to form because we've got a carboxylic acid and an alcohol. If I label those groups, we've got carboxylic acid here. So carboxylic acid I'll just write as Ca, and an alcohol. So alcohol there. That's going to form an ester group. So if we're having a dimer, and a dimer means that it's 2 identical groups attached, it's going to look a bit like this with our partial A attached either side. I will identify the ester links in just a minute. So if I'm showing the ester links, here is one ester link and here is our second. And we can see that this molecule is symmetrical, which is what a dimer is. 2 identical groups. Very easy to split it down the middle and make it symmetrical. As we're forming an ester, this is a condensation reaction, so we would form water as a byproduct. The type of reaction we can say is esterification because we are forming an ester. To get the 3 marks for this question, we haven't actually finished. We need to balance the equation by writing a 2 here to get our 2 H2O molecules. So again, getting our 3 marks, you get a mark for your basic equation, a mark for getting all of the compounds correct, mark for balancing it, and a mark for naming the type of reaction and that being correct. C. Chromium 3-piclinate shown below is a neutral complex that can be prepared from the weak acid piclonic acid. Chromium 3-piclinate is used in tablets as a nutritional supplement for chromium. Part 1. Draw the structure of the ligand in chromium 3-piclinate. The key word in this question is that we're drawing the structure of a ligand. A ligand is in your transition element or metal topic, and we can identify the ligands because they are attached to your metal ion. We have 3 ligands and they are all identical. So it's 1 ligand replicated 3 times. Here I'm just representing them, and that means because they're all the same, we can very easily draw the structure. If we look at the diagram, they're going to look a bit like this. If we draw it at a different orientation, with making sure that we have our N attached, that our double bonds are in the right place, and that we have the rest of the molecule correct. We would then have a negative charge on our oxygen because the chromium would be having a positive charge and the ligand has to have a negative charge in that case. To get the mark for this part of the question, you need to make sure that you've drawn the structure of your ligand completely correct, and that will get you the mark. In part 2, we're told that a typical tablet of chromium 3-piclinate contains 200 micrograms of chromium. Calculate the mass in grams of chromium 3-piclinate in a typical tablet. 1 microgram is 10 to the negative 6 grams. Give your answer to 3 significant figures. To start, let's identify the key pieces of information we've been given in part 2. Our first key piece of information is 200 micrograms of chromium. We're also given the scale to use when converting micrograms into grams, and the fact that we need to give our answer to 3 significant figures. If we start by working out the relative formula mass of a ligand, we can then work out the relative formula mass of the whole neutral complex. So, to begin, if we look at one ligand here, we can identify how many carbon atoms there are and write a little list. So, let's count them. 1, 2, 3, 4, 5, 6. So there are 6 carbon atoms. Then, looking at hydrogens, we can draw them as little sticks. So 1, 2, 3, 4. There are 4. Next, moving on to the number of oxygens there are. Well, this is slightly easier to identify. We have 1, 2 oxygens. Writing that in our list, 2. And then finally, how many nitrogens? Well, we've got 1 there in our complex. So nitrogens, 1. Working out the relative formula mass, that gets us 6 times 12 plus 4 plus 16 times 2 plus 14, which gives us 122 as the relative formula mass of one ligand. There are 3 ligands in this complex, so we do 122 multiplied by 3, and then we need to add the relative formula mass of chromium, and that is 52. That gives us a relative formula mass of 418 for the whole complex. Next, we need to take the 200 micrograms of chromium, and we need to work out the number of moles using this. So we take 200, we multiply by 10 to the negative 6, and we divide by 52, because we're told that it's the mass of chromium, and 52 is the relative formula mass of chromium. That gives us 3.85 times 10 to the negative 6 moles. And we can then take the 418 and multiply by 3.85 times 10 to the negative 6. And that gives us 1.61 times 10 to the negative 3 moles if we were to write our answer to 3 significant figures, which is what the question is asking. So 1.61 times 10 to the negative 3. The equation triangle that I have used to answer number 2 is as follows. Mass over relative formula mass multiplied by moles. The way a equation triangle works is you cover up the item you're trying to work out, and what's left is the equation you will use. This question, in order to get our 2 marks, we first need to work out the relative formula mass of the complex, work out our moles. That together gets us our first mark, and then we multiply these to get our moles. Writing that to the right number of significant figures gets you your second mark. This question is about organic molecules that have a strong smell. Part A. Thiols are foul-smelling organic sulfur compounds with the functional group SH. Butane 1-thiol, shown below, contributes to the strong smell of skunks. Part 1. Thiols are weak acids. Write the expression for the acid dissociation constant Ka for butane 1-thiol. The general expression for Ka is H plus A minus over HA. So that means that it's H plus and then a salt, which is A minus, over the compound. So if we were to apply this to butane 1-thiol, we would get Ka equals H plus and then C4H9S minus over C4H9SH. We can see that another way of looking at this equation is that the denominator is equal to both parts of the numerator. To get the mark for this question, you have to have the whole Ka expression correct. Part 2, thiols react with carboxylic acids to form thioesters. Write an expression for the reaction of butane-1-thiol with ethanoic acid. Use structures of all organic compounds with the functional groups clearly displayed. If we start by writing out our reactants, butane-1-thiol would be CH3, CH2, 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 SH, plus ethanoic acid, which we would write slightly differently to represent the carboxylic acid functional group. If I highlight this, here is the carboxylic acid functional group, and the question is asking for all organic compounds with the functional groups clearly displayed. If we then write our products, well, we're forming a thioester. So a thioester, that means it's a similar ester group, and the general ester group would be as follows, with an R attached either side. But it's a thioester, so it's going to have sulfur featured, and it would appear as follows, with the CH3 coming from the ethanoic acid, C double bond O S for the thioester, and then CH2, 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 CH3 from the butane, plus water. Because it's esterification, you always form water, it's a condensation reaction. For this question, you get a mark for the general equation being correct, and then you get a mark for your functional groups being clearly displayed. So in the ethanoic acid and your thioester link being correct. Part 3. When beer is exposed to light, 3-methyl-but-2-ene-1-thiol is formed, which gives an unpleasant smell and flavour to the beer. Draw the skeletal formula of 3-methyl-but-2-ene-1-thiol. If we break down the question and we look at the key pieces of information, we need to draw the skeletal formula. Then we can look at the individual parts that make up 3-methyl-but-2-ene-1-thiol. So looking at 3-methyl, well, that means it's going to have a methyl group on the third carbon. If we draw out but-2-ene, that would look like this, skeletally, with 4 carbons, 1, 2, 3, 4. Then we can draw the 3-methyl group on maybe carbon number 3. That could be our carbon number 3. Then our thiol group, well, a thiol group, that is an SH group, and it would be on the first carbon. So if here is number 3, then here would be number 1. So if we draw that in black to answer the question, our 3-methyl-but-2-ene-1-thiol, drawn skeletally, looks like this. To get your mark for this question, the whole structure needs to be correct and in skeletal form. Part 4. Propane-1,3-dithiol reacts with carbonyl compounds in a condensation reaction to form a cyclic organic sulfur product. Write an equation for the reaction of propane-1,3-dithiol with propanone. Use structures for organic compounds. So if we begin by writing or drawing out our reactants, we firstly have propanone, which would look like this, drawn skeletally, with 3 carbons and a ketone group. Next, we would draw propane-1,3-dithiol, which would look like this, with our propane and 2 thiol groups attached to the ends. This would produce what we're told in the question, a cyclic organic sulfur product. So a cyclic product, that is going to have to show this in our product. And it would look like this if we were to combine the propanone and the propane 1,3-dithiol. We're also told that it's a condensation reaction, therefore our second product would be water. To get the 2 marks for this question, you get 1 mark for your reactants being correct and 1 mark for your products being correct. B. The structures for 6 naturally occurring organic compounds with pleasant smells, B to G, are shown below. The common names in brackets relate to their source and smell. Explain how chemical tests would allow each compound to be distinguished from the other compounds. In your answer, include essential details for all test procedures and observations. Details of apparatus and quantities are not required. So a question like this is quite a common one, and it's asking about tests for functional groups. So whenever you're asked this type of question, look at the compounds and label the functional groups, because you get marks for this, and that means you don't need to write a lengthy explanation. You can just simply label them. So if we start with B, we've got 2 alkene groups. We can just write that here. Then we've got an alcohol group, but you need to be more specific when talking about alcohols because there are 3 different types. This is a tertiary alcohol because there are 3 R groups attached. 1, 2, 3. Moving on to C, we've got 1, 2 alkene groups like B. And we have an aldehyde group. It's an aldehyde because the carbonyl group is on the end of the molecule. And there's no OH attached, so it's not carboxylic acid. In D, we've got 2 alkene groups, like before. And then we've got an alcohol group, but this time our alcohol is a primary alcohol because there is 1 R group attached. Moving on to E, we've got a ketone, and we've only got a ketone in compound E as our functional group. In F, we've only got an alcohol. Again, making it more specific, we've got a secondary alcohol because we have 2 R groups attached to our alcohol group. In G, we've got 1, 2 alkene groups, and we have a ketone. Next, we need to lay out our testing in an effective way. An effective way would be as a flowchart or a table. I'm going to draw a table. Our first test, because we've got a lot of alkene groups, is bromine water. And if there's an alkene group, it will decolorize bromine water. So you could also write that this is a test for alkenes, just to show to the examiner you really know what you're talking about. And then if we write our compounds, and we can make this into a table. It doesn't need to be really smart or neat. Obviously a ruler would be helpful, but it's okay. So B is a positive result because there is alkene group like C and D. There is no alkene group in E or F, but there is in G. So you can see how labeling the functional groups makes this a lot easier to do. Then our next test would be 2,4-DNP, and it's an orange precipitate we're looking for, and that would be a test for a carbonyl group. So if we write that on the side. So the carbonyl groups we have are in C, the aldehyde. We also have one in E, the ketone, and one in G, another ketone. Our next test could be Tollens reagent, and that would be a silver mirror produced, and that's a test for an aldehyde. There is only 1 aldehyde out of our compounds, and that is C. So we would put a tick next to C. Finally, we would test with acidified dichromate ions, and we would hope for a colour change from orange to green, and that is a test for primary, secondary alcohols and aldehydes. So if we tick, we've got tertiary alcohol on B, so there's no oxidation that occurs, so we won't have a result. In C, we've got an aldehyde, so we would have a result. In D, we've got a primary alcohol, so that would be a positive result. F, secondary alcohol, that would also produce a result. And there we have it. This is a level response question, so there aren't exact marks. You get marks for detail and how you've answered the question. So labelling your functional groups, that gets you your first 2 marks. If you've missed one out or you've only labelled alkenes once, it depends on the examiner whether you'd get that mark. Your next marks are for the tests that you do and the positive results that you're saying. They're the next 4 marks, and then if you've correctly put ticks and crosses or left them blank, we could write crosses just to confirm that we know they would have no reaction. But it's not essential. Okay, and this is how you answer part B.